Hello guys, let us start part number 2 of partial differential equations or differential equations, how it can play a role in science, technology and engineering. So as I promised in the previous class, means in the part number 1, today we are trying to solve the highly nonlinear partial differential equations with finite difference method. See now, what we had in the part number 1, will just give the brief review of the previous part 1 lectures. So I request all the students, those who had absent or those who are not looking my videos of the part number 1, please go through the part number 1 and then go for the part number 2, then only you can understand what we did in the basic in the part number 1. We are trying to develop one mathematical model, which was the partial differential equations. Okay, by taking the petrophysical parameters. Just have a look in the slide what we did in the previous lecture. Just look here. Those who are not looking my previous lecture, just come up here. So mathematical modeling and simulation for one-dimensional two-phase fluid flow in petroleum reservoir. So what was our aim in the previous lecture was that we are trying to formulate one mathematical model, which is called the mathematical modeling, right? By taking the petrophysical parameters. So we had developed in the previous lecture, it was the first order partial differential equation, which was the highly nonlinear partial differential equations. Second objective was that the second objective, today we'll try to solve it. Second objective is we are trying to solve the mathematical model, whatever we have developed in the previous class. Okay. Now come up here. We had developed in the last class by taking care of all the petrophysical parameters. Those who are not absent in the previous lecture, please come up here. So this was the partial differential equation we have developed. Okay. Now look here in the part number 1. Just listen here. In the part number 1. In the part 1, what we did? We have formulation, right? We have formulated mathematical model. We had formulated mathematical model. We did this one. What are the parameters? What are the parameters we have considered to formulate the mathematical model? What was it? It was first order. It was first order partial differential equation. This is a non-linear partial differential equations. The part number 1, what we did, we have formulated mathematical model. It was a first order partial differential equations and it is a non-linear partial differential equations. What are the parameters? What are the parameters? What were the parameters? The parameters. What were the parameters? Number 1 parameters was porosity. We take the consideration porosity as a parameter. Next, we took relative permeability. Relative permeability. We took relative permeability. C. We took permeability. Number 3, we took the fluid viscosity. We took the fluid viscosity. We took the density. We took the density. Okay. and we took the length of the system we took the time, right? We took the time. What are the notations we have here? We'll do the notation here. This is the phi. If it is relative permeability, we took the small k. If it is a permeability, the notation is capital K, right? If it is a viscosity, we took the mu. If it is density, it is the rho. If it is a length of the system, it is x. If it is time, we have, this is t. How many parameters? 1, 2, 3, 4, 5, 6, 7. Total 7 parameters we have considered after considering porosity, relative permeability, fluid viscosity, density, length of the system, and time. After taking care of all these things, what we have observed here, we have got, this is a final partial nonlinear differential equations, right? Here, you can get here number of parameters, whatever I have described here, right? Here again, the S is the saturations. Again, I forgot to mention here. Here we can get one more is that in the I, this is called a saturation. It is a saturation. It may be water saturation, it may be gas saturation are here. So total 8 parameters we have considered in our model. So here, what we took here, we took the permeability, we took the relative permeability, we took the porosity. Total 8 petrophysical parameters we have considered. After taking the consideration of all these petrophysical parameters of a petroleum reservoir system, we have finally developed one partial differential equations, and this is our partial differential equation, which is a first order, and it is highly nonlinear partial differential equations. Now, in part number 2, that means today we want to do the simulation. The part number 1 was that we have developed one mathematical model. That model was first order partial highly nonlinear differential equations. What are the parameters? We took total 8 parameters here. We took total 8 parameters. These parameters are the responsible for the fluid movement in the petroleum reservoir system. Okay, so today our plan is that how we can solve this highly nonlinear first order partial differential equations. So our planning is that to solve it, right? We want to find out the solutions of water saturations, which is distributed along time and length. Our plan is again to solve this partial differential equations, and our plan is to get a distribution of the pressure, right, in time and length, how it is distributed. Now, as I told you that there are a number of methods to solve the partial differential equations, right? So we have mainly classified 2 parts. We can classify mainly 2 parts. So now, finally, we have got the mathematical model. Now we have mathematical model. Now we have mathematical model by considering all these parameters. Okay. Now to solve it, we have 2 forms of here. One is analytical. Second is numerical. This will give actual solution. But it will give approx solutions. Now you may confuse that if I can get the exact solution by the help of analytical methods, why I am trying to solve with the help of numerical methods. The answer is very simple. The analytical methods has lots of limitations. The analytical method may not be applicable, or it may not be possible to apply the analytical method to solve the engineering problems. Here, our problem is engineering problem. There are 8 parameters which are highly nonlinear first order partial differential equations, and coefficients are variables. It means that the analytical method is not possible to apply in our model. That's why we have to go for the numerical methods. Now, what are the different type of numerical methods we can adopt? Number one is we can adopt finite difference method. We can adopt finite difference. We can adopt finite difference method. We can adopt finite elements method. We can adopt finite elements method. We can adopt finite volume methods. But today's lecture, I am planning to discuss the finite difference method. How we can solve the highly nonlinear partial differential equations with the help of finite difference method. How we can solve it. This is our first priority. Next, it may be solved by the finite volume. It may be solved by the finite elements method. So our simulation technique we are planning to use in our this lecture, especially finite difference method. Now, what is the finite difference method? What is the finite difference methods? What is the role of the finite difference here, which is very much important for all of us? What is the role of the finite difference method? What is the role of finite difference? What it will do? It is very simple. It is going to do analytic to discrete, right? It is going to be discrete, right? So if I use here finite difference method, analytical is going to become in discrete form. It means that if there is a differential equation del u by del x, I want to write in the form of discrete form, right? If there is a partial differential equation, this one, I want to write in the discrete form. If there is a partial derivative del u del t, I want to write in the term of discrete form. If there is a second order partial differential equation, I want to write in the discrete form with the help of finite difference, right? I want to write in the discrete form. Now, how it can be possible to write in the discrete form or not, right? Now, I want to write here discretization. I want to put here discretization here. It is in the form of discretization form. Analytic to discretization form. Now come up here. In my slide, if I come up in my slide, you can see here. You can see here. This is the partial derivative with respect to x. The finite different approximation we can write in this form. This is called the forward type. First order, because it is del u by del x. Next, del u by del x, I can write this first order partial differentiation in the form of finite difference form, which is backward form, and it is also first order. Come up here, central difference form, where I can write this first order partial differential equation in the form of discrete form. Same thing here, second order, use the finite difference, I can write in the form of discrete form. This is the first order with respect to t, I can write in the form of discrete form. This is the first order with respect to t, I can write in the discrete form. Same thing here with respect to t, first order, central, I can write in the form of discrete form. Same thing, this is second order with respect to t, I can write in the form of discrete form. So, what is our aim? Our aim was that I want to do the simulation of the model we have developed. To do the simulations, we have number of methods. One of the method is analytical methods. Second is our numerical methods. Since our engineering problems are very critical and it is highly nonlinear, the analytical method is not possible to apply to solve these type of problems. That's why we are planning to apply the numerical techniques. The numerical technique also we have number of methods. One of them is finite difference, right? And it may be finite elements, it may be finite volumes. So we'll come one by one. In a today's lecture, we're planning to solve with the help of finite difference method. What is the finite difference? It is very simple. It will do the discretization. If it is del u by del x, apply the finite difference, it is going to be in discrete form. If it is del u by del x, in backward, forward, I can get a discrete form as I have shown here on a slide. If I do the del u by del t, I can get three types of discrete form: forward, backward, and central. Same thing I can do in second order partial differential differentiation with respect to t or with respect to x. But what it will do exactly in a discrete form means this is in the equation form. Now, if I want to represent it is graphically, I am not going to write here because I have already shown here in a table. So I have shown a discrete form in a table. I have shown discrete form. I have shown discrete form. I have shown in a discrete form. So you can get in the table, right? In that table, I have already shared to you. So you can get all these things in this table. So this is in the form of continuous form. I can get discrete form, continuous form, discrete form, continuous form, discrete form, continuous form, discrete form. How it is coming? We apply the finite difference approximations. Now, this is the equation form. Now, how it is represented in the form of graphical case. Now, come up here. In terms of graphical representation of the discrete form, suppose I want to represent graphical representation. Suppose I want to do this is in graphical representations. How I can do it? Let us try to discretize it, right? Let us try to do the discretization. Suppose I have here, suppose I want to do the discretization here. For example, I have suppose this here. Sorry. So I have here this. Suppose I want square or this. For example, I have this one. Suppose here, right? For example, this represent suppose I, and this represent in this suppose end. Some books they can write in ing also. Suppose this is in terms of length. And suppose it is n is time. Sometimes if it is length, they write it is x, so don't confuse. Now it is n. Suppose if I try it is in terms of time. Suppose it is time. Some they write it is in terms of t. Right? Suppose here along this the I will move. It means I can move the x. Suppose I have discretized here like this. For example, suppose my figure is not coming perfectly, it should be straight line like this. Suppose I have discretized. I am doing the here discretization here. It should be perfect. It should be a perfectly straight line, but my figures are not coming. So I have discretized. Suppose it was x0. It is x1, x2, x3, x4. x5 dot I can do the discretization. Same thing if I do the discretization of the time scale. If I do the discretization of the time scale like this, right? Suppose it is T0, T1, T2 up to like this. We can do the discretization. So it is represented by I and Z. Suppose this U is the function of S and T, right? U is the function of x and t, where x represent the length and t represent time. For example, suppose this location is I comma n. I comma n. Because along this axis, I will move. Along this axis, n will move. For example, if I write here, this is u. If I represent the suffix as a I and superscript as a time. If I move along the top, the u superscript will increase or decrease. If I move left, right, then the subscript I will move more and less. If I move right side, then I can get I plus 1. If I move left side, I can get I minus 1. If I move above, then I can get I is constant because I am not moving left and right. If I am not moving left and right, then I will be constant. Now, if I move along top to bottom, then n is going to be changed because the n represent top to bottom, I represent left to right here. Now, if I take this point, if I take this is u, I plus 1 and n is constant here. Now, if I move here, this point will be u will be I minus 1, n is constant. Because we are not moving up and down, we are moving left to right. Only I is decreasing 1 and increasing 1. Now, if I move top, if I move here, I am not moving left and right. I am moving top to bottom. Means n plus 1, right? If I move bottom, I can get ui n minus 1. So I can get ui n minus 1. So this process is called the discretization. So we have discretized the x in number of points. We have discretized the m in number of points. So now, if this point is I comma n, means uin, then if I move left of this point, then I will be decreased by 1. If I move right of this point, then I will be decreased by or increased by 1. If I move above this point, I can get n plus 1. If I move below this point, I can get n minus I. That's why here, if I want to find out the differentiation this, if I'm find to differentiation this, how I can represent from the graph? See, the distance between two consecutive points along x-axis is represented by delta x. Now, the distance between 2 points along the y-axis is represented by delta t, right? It is represented by delta t. The distance between two consecutive points is delta x along this axis. The distance between two consecutive along this y-axis is delta t. Okay. Now, I want to find out the value of del u del x, right? It was written this u with respect to x, right? It was written that del x u I plus 1 and minus u I n. It was written here, right? U I plus 1 and minus u I n delta x. It means what? Where I can get this point? Where I can get this point? The point partial differentiation with respect to x can be calculated by taking the value of this, right? This is the point. This is the point where I can get the value of ui plus 1n. And this is the point. This is the point where I can get ui n by delta x. What is the delta x? Delta x is the distance between two consecutive points along x-axis. Now, if I try to find out del u by del t, it means partial differentiation with respect to t. What I can get here, it is delta t, okay? Since it is with respect to t, it is going to move up and down. That's why I will be constant here. So I can get n plus 1 minus uin. How I can get this value? The value we can calculate from this point, right? This point minus this point divided by delta t. Similarly, we can calculate the value of this, value of this, value of this. All the value can be calculated by taking the simple example of this graphical representations. Okay. Now if I have the values of at the boundaries of the grid points, if I have the values where I have put it here red circle, if I have the values of these red angles at the boundaries, suppose I have the values, right? If I have the values at the all point, I have put it here red round here, 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 here. If these values are given to you, then this is called the boundary value problem, right? Now, if the values of the functions is given at the initial level, so we can get also initial value problems. Okay, so I hope you have understood how we can do the discretization of a given continuous function to the discrete form with the help of finite difference technique. So now let us move. Now we are planning to write, instead of del RC by del X, I want to write in the form of this. I want to write in the form of the grid system, because it is a highly nonlinear partial differential equations. It is not possible to solve by our analytical method. So I need to discretize. I need to discretize where it is written partial differentiation with respect to X. So I have to write in a discrete form. Same thing here, it is the partial differentiation with respect to X. So I have to write in the form of discrete form. Same thing here, I have to do the partial differentiation with respect to T, here also with respect to T. So I need to transform in the form of discrete form. Then accordingly, I need to find out the value of del RC by del X. How I can find out this grid system. Now look here in my slide. I'll discuss after this slide. Come up here. See here. We have here the partial differential equation, which is called our mathematical model. Next step is we have to impose now initial and boundary condition. So come up in the next slide here. Initial and boundary condition. What was the initial and boundary conditions? If the values of the grid at the boundaries are known, then we can apply all these boundary conditions. If the initial stage the values are given, then also we can apply to get the solutions of the given partial differential equations. Now look here, the initial conditions are, suppose water saturation or gas saturation. So, right? Suppose S is a saturation. Initially, T is equal to 0 here. But for any value of X, T is equal to 0 means what? I have to take this ground. Suppose if we consider this is here, T is equal to 0 here. For any value of X, suppose for any value of X, suppose it is the values are given here, values are given here. All the boundary values are given here for any value of X. For example, the water saturation or gas saturation means saturations are given. What is the given here? It is defined by a function gx. Instead of value, we have to define one function gx. Okay. Next, the condition at the outlet end of the system. See, density is suppose constant. Density of the fluid is suppose constant. At the outlet means for example here, if I consider here, this is the capillary tube which is in the petroleum reservoir system. Here we have suppose that here, right? So now if I took this is inlet, suppose this is inlet, means fluid can flow this through porous media. Suppose this is the porous media. This is called the outlet. This is called the outlet. Now, outlet means suppose this total length is capital L. We are talking about that the outlet, the density the density, right, for any time is constant. We assume this one, right? We assume this is constant. Come up here. This is constant. A constant mass injection rate. Mass injection rate can be defined like this. Capital G is called the mass injection rate. The formula is given by minus density, relative permeability divided by viscosity, del phi by del x. This also constant. See, these are the all initial conditions. Now come up, the boundary conditions are here. Now if only the Z phase, so we are taking two phase, I phase and J phase. I means suppose oil, J means suppose water. Suppose oil and water. Okay. However, then Gi and Gs, this is the injection rate, mass injection rate, and this is the saturation equal to 0 if phase 1 and phase 2 are not equal. If there is two phases, for example, water phase and oil phase, or oil phase or gas phase. In that case, if they are not equal, means if we have two different phases, oil and gas, or water and gas, or water and oil, then we assume that the saturation of Z is equal to 1 because we have only injected J. Suppose I have injected water. That saturation at beginning level, x is equal to 0 means at the first inlet system, saturation is equal to 1. And this constant. So this is our problem statement and initial and boundary condition. We'll consider this boundary condition. Now come up here. What are the general methods? I have already discussed to you analytical method and numerical method. So finite difference, finite elements, finite volumes, but this Crank-Nicolson is also one type of finite difference method. Spectral method is very modern method, and mass-free, these two are very new methods. But at present, today's lecture, we're talking about the finite difference method. Okay, and what is the role of the finite difference? I have already explained to you. It is going to be transformed from analytical method continuous to the discrete form. Now here, general method, again, in the case of finite difference method, we have mainly two cases. One is called the explicit method, right? Using a forward difference. Got here? Just look my table here. Forward difference, backward difference, and central difference. Now, if we talk about the explicit method, we use forward difference. Okay? Forward time central space method. It means numerically unstable solutions. So if it is unstable, we are not planning to apply any type of explicit method. What are the inputs here? We use the forward difference during the discretization of the partial differentiations. Be careful here. Now, if I want to get the value of, in this particular points, I need the value of this, I need the value of this, I need the value of this, then we can find out the value of this one. So what is R here? Here R is, don't confuse here, what is R here? Here R is equal to, here R is equal to, here R is equal to K by H square. What is the K? Here K is delta X is equal to, delta X is equal to H, and delta T is equal to K. It is increment along x-axis, it is increment along t-axis here. Okay, so we use the forward difference, right? It is not stable, so we don't use here. So I can get the value of this once I have this value, and this value, or I can get this value if I have this value, and this value. Okay, now come up here. Implicit method, we use the backward difference method. So I hope we are very much clear how to discretize backward and forward here. Okay, backward I can apply here, forward we use previous methods here, numerically stable solutions. Okay, it means I can get the value of this if I have value of this, and value of this. What is the value of R? It is K by H square, right? Next, come up here, Crank-Nicolson methods used for central difference. What is the central difference? This is the central difference. If I use partial differentiation with respect to x, I have to apply this discretized method, right? If I want to use the partial differentiation with respect to t, then I have to apply these methods, central difference method. If I use the central difference method, then I can get the Crank-Nicolson's method, right? In the case of explicit, we apply the forward difference method, which is not stable. In case of implicit method, we use the backward difference method, right, which is a stable. But Crank-Nicolson is more stable because we use the discretization technique in the form of central difference form. Here, this R also represent H by K square, K by H square. K represent increment in time, H represent increment in length. So by using the finite difference method, we can get three types of discretizations equation. One is implicit, second is explicit, and third is Crank-Nicolson's methods. Okay, we are trying to use here Crank-Nicolson method to get the solutions. Now come up here. In case of explicit method, it is not stable. Look here. These are the explicit solutions and green is the exact solutions. So it is up and down, it is not stable. In the case of implicit method, look here, exact is the green, red is the implicit solution, so it is stable. In the case of Crank-Nicolson's method, also we can get exact solutions and Crank-Nicolson solutions are matching here, but in the case of explicit method, the calculated solution is not stable. So we don't want to use the explicit method. We can use either implicit or we can use the Crank-Nicolson's method here. Now come up here, numerical solutions. So this was the equation in the form of analytical form, which is the functions of density, which is the functions of permeability, which is the functions of relative permeability, which is the function of viscosity, which is the functions of porosity, which is the functions of saturations in wetting and non-wetting phase, which is the functions of time and functions of length. Now, I want to replace these partial differentiations in the form of discrete form. Look here. I have just discretized this one. I have just discretized this one. I have just discretized this one in the form of grid system. Those who have understood my grid system, it is not difficult to understand how this del RC by del X is here discretized, right? Same thing here, how I have written the discretizations of this equation in the form of grid system. Same thing here, how can I discretize in the form of grid system? So from this continuous equations, we have discretized in the form of discrete form. Okay, now it is very difficult to write every time to represent all these things. That's why what I'm doing, I have represented this is capital E, I have represented this is capital F, and this is delta T by delta X is a beta, right? Here I have do the representations here, right? This is I have represented this in different form here. This is E, this is F, and this is beta. Now, the equation for the factor beta is as follows. Delta T by delta X, how it is coming? It is coming from here. If I do the simplification of these equations, I can get delta T by delta X, so I can get these equations. Now, look here, I phase and N phase. Everything is now it is. If I move left and right, I can get increase or decrease with I. If I move up and down, I can get increase and decrease in N, N plus 1 and minus 1. Here, if I move left and right, I can get I minus 1, I plus 1. Okay. Now come up here. After doing all these things here, equation of the rate of change of pressure with respect to length. So from this equation, from these equations, I take out RCIN, right? If I take RCIN, what I can get here, this is the equation. What is capital E? What is the capital F? What is the capital beta? This mentioned here. This capital E, capital F, and beta is come up here. So RCIN, this represent rate of change of pressure with respect to length. Just look here. What was the RC? you can get in the previous slide here. In the equations I did here, RC, rate of change of pressure, capillary pressure, PC means capillary pressure, rate of change of capillary pressure with respect to length. So I need to find out this R. So after doing the discretization by using the finite difference method, I can get the equation where the boundary conditions can be applied to get the value of rate of change of pressure with respect to length. Same thing from the same equation, from this equation, let us calculate the equation of water saturations, right? SWYN plus 1. So if I move right, I can get I plus 1. If I move left side, I can get I minus 1. Or if I move top and bottom, I can get N plus 1 and N minus 1. It means that now, if I get the initial condition and boundary condition, the rate of change of pressure with respect to length can be calculated. The water saturations can be calculated if I have initial and boundary condition. Let us look now. What is the input parameters? Look here. I have now two equations. I can get the rate of change of pressure with respect to length. I can get a rate of change of pressure, means capillary pressure, with respect to length. Same thing, I can find out the water saturation, right, with respect to length here. Now, let us try to impose boundary condition and initial conditions. Now, how it is coming? How it is coming? These input parameters and boundary values are coming. Basically, if I do the experiment, if I can find out the boundary condition and initial conditions in the laboratory, then I can get our simulation will be perfect. Otherwise, we need to take the help of available in the literature, which is already published for the particular reservoir. For example, we have these values from the available publications. We take the help of them. We take the two phases. The porosity was, we took 0.24. Inlet water saturation, I take 0.25. In initial water saturations, initial oil saturation, I took this much. Inlet mass water, we took this one. Now, you may ask how you are taking all these things. We took these values because these values are calculated experimentally, and these are already published. So we took the help of these publications and we try to impose the boundary conditions. We try to impose the initial conditions. Hence, we can find out the pressure distributions with respect to length and water saturation distribution with respect to length. How it is coming? Because numerical technique, the finite difference method required the boundary values, and boundary values can be calculated in laboratory. Then we can get most accurate solutions. If it is not available in laboratory, so we have to take the help of literatures where it is available. So delta T means time increment. It is 0.05 hours. Delta X means length, X means increment, 0.025 beta, which is the delta T by delta X. Length of the system is 3 feet. Pressure, initial pressure is 14.7 psi. Density of the water, 62.4 lb cubic feet. The density of the oil, 55.0 lb per cubic feet. Viscosity of the water, 0.8 cubic, right? So viscosity of oil, we took this one, and this is the initial permeability. By taking input all these things, then I can get the value of sense of pressure. I can get the value of water saturations. Now come up here. This graph. If we look at the graph here, the force is coming the force equations where we can get the pressure distribution here. So what we do here, 8 hours, 16 hours, 32 hours, 48 hours, and 96 hours. If I use all this time bound, I can get the pressure. See, where it is the highest the time, we can get the less pressure. Where is the lowest hour, we can get the highest pressures. And all are approaching towards the some particular point if I increase the length of this one. Same thing in the case of water saturations, right? 96 hours, 48 hours, 32 hours, and 16 hours. So we can get water saturations. We can get the water saturations from where it is coming. It is coming water saturation from the second equations, and sense of pressure, it is coming from the first equations. Now, I hope those who have looked my part 1 video, I hope they understood that how we have developed the partial differential equation by taking the petrophysical parameters, right? Porosity, permeability, relative permeability. After taking care of all the reservoir parameters, we developed one mathematical model, which was the highly nonlinear first order partial differential equation. This was the mathematical model we have developed. Now we have to solve it. How to solve it? By doing the finite difference method. Why it is not possible by doing the our traditional method? Because it is a highly nonlinear, right? It is not possible to solve the analytical methods. That's why we took the help of finite difference while it is in a discretized form. Okay, after taking the discretizations, we have to apply the initial and boundary conditions. Applying the initial and boundary conditions from the first equation, we can get a change of pressure. From the second equations, we can get what we can get from the second equations. We can get the water saturation distributions. I hope the students, those who are in the very beginning stage, they have understood that how differential equation is important in science, technology, and engineering. It is an integrated approach to develop the differential equations. We should understand what are the science behind inside the system. If I have understood the system, then I can develop, means I can identify the parameters. For example, in our case, the petrophysical parameters are porosity, permeability, viscosity, density, capillary pressure, length, water saturations, all other parameters. Then we have developed one non-linear partial differential equations. This equation is called the mathematical model, and the process is called the mathematical modeling. Okay, now we want to solve it. We have two options. One is analytical method, second is numerical method. Since it is a non-linear, so we are not able to solve by using the analytical method. So we took numerical methods. There are a number of methods: finite elements, finite difference, finite volumes, integral equations, everything are there. But we take here basically the finite difference method. Here we do the discretizations of del u by del x in the form of grid system. We do the discretizations of del u by del t in the form of grid system. Then our model has been discretized in the grid system. Okay. Then we develop two equations in a discrete form. One equation represents the sense of pressure distributions. Second equation represents the water saturation distributions. Now, by using the initial and boundary conditions, we can find out the sense of pressures with respect to length, and we can find out the water saturation distribution with respect to length. So finally, what we had, we got these two graphs. So I hope you have understood here. So I will do various type of mathematical modeling and simulations videos. I hope that you have got a basic idea what is the mathematical modeling and what is the simulations, and what is the role of differential equations, how it can be integrated the science, technology, and engineering for the benefit of the society. Thank you very much. Next class will come up with another problems. What is the importance, how we can do the integrated study, how interdisciplinary study can only help the society, will come in the next video. Thank you very much. Today I'll stop here. Thank you very much. We'll meet in the next lecture.